Hi, everybody, and welcome to our next video. So for today's topic, we are going to be starting our third unit, and the focus of this unit is really about taking all the information that we can possibly gather about a function or its derivative or even its second derivative, and taking all that information, compiling it together to gather uh, as clear a picture and as much information as possible about what the graph of that original function looks like. So we're really going to be going through a bunch of different processes to figure out exactly where all the twists and turns, peaks and valleys, minimums, maximums, where a graph increases, decreases, the overall general shape of the graph. We want to try and put all of that information together with the end goal of being able to really come up with a really accurate view or picture of what a function's graph looks like. And then we're also going to take all of that information and look at it through the lens of real-world applications and what the implications of all those twists and turns on a graph has for when those equations represent real-life quantities. So to begin that focus and that look, today we're going to talk about a couple of things. So first, we're going to look at the extrema on a graph, so where mins and maxes are. And then we're also going to look at an application for this information called mean value theorem and Rolle's theorem. So to get us started, we're really going to talk about the connection between a function's graph and the actual equation and the derivatives that follow. So to get us started, we're going to first focus on being able to find the extrema of a function. So one major application of a derivative is being able to describe how a quantity changes. So that means whether the function's increasing on an interval or decreasing on an interval. So if we're concerned on where a function is increasing, then naturally we would be interested in what happens to the function as it continues to increase and where it eventually reaches its maximum value, if it ever does. So this is just kind of a natural next step. Now that we know how to figure out where a function increases, now we want to talk about where does it reach its maximum value or vice versa. So the extrema of a function, this is an all-encompassing term, and it's referring to the maximum or minimum values of a function. But there's two types of extrema that we talk about, and it's really important that you know which one it is we're referring to, because depending on which type we're looking for, we actually find them in different but kind of similar ways. So it is important that we know exactly what kind of extrema it is that we are talking about. So the first type is a relative extrema. So a relative extrema are another name they go by are local minimum or maximums. So minima and maxima are the plural version of those words, just in case you're wondering. Thank you, Latin. So for relative extrema, it basically just represents those low or high points on one local portion of a graph. We can really look for them easily on a graph by just figuring out where the graph changes directions. So anytime that a graph has a turning point, so I go from increasing to decreasing, decreasing to increasing, these places where we make that change are those relative extrema. Now, they're not always smooth turns. Sometimes we have these sharp turns, but these guys are still places where the graph has changed direction. So we still have to account for those kinds of points. So those are all relative extrema. Those have special implications as far as calculus is concerned. But then the second type are referred to as absolute extrema. So for absolute extrema, it's kind of in the name. We're referring to the absolute lowest or highest values anywhere on a graph. Okay, so now when we do this, we're typically thinking about one particular interval. So on a specific interval, what is the absolute smallest value and highest value that the graph has between two x values? Now, sometimes that interval is the entire function's domain. Some functions have those. This is typically more of what you guys have looked at in the past, because a lot of extrema deal with like a quadratic function's turning point is the highest or lowest anywhere on the graph. But now we have to be able to specify the difference. So there are going to be some cases where a function on a given interval does not have a minimum and a maximum, or it may not have either of them. That's what these graphs are depicting here, It actually all depends on the interval and how the function behaves on that given interval. So for example, this first guy, this is actually demonstrating a function that has both a minimum and a maximum on the interval. So we're going from -1 to 2. And notice that both endpoints are closed points. So the function is defined there. And it just so happens that one endpoint is the maximum. And then in the middle of the interval, we reach a minimum value. So that's one way that this could happen. But depending on the interval, the information that we're given, we could be working on an open interval, which means the function's not including the endpoints. So notice that those are open dots now. So that means neither of those could possibly be candidates for a minimum or a maximum because we're not actually including those points. So in this case, the minimum is still occurring at this turning point down here, but we don't actually have a maximum here because the issue then becomes, well, what is the point right before that hole? And remember, theoretically, we can't figure that out because there's always an infinite number of values between any two values on the real number line. So we can't actually determine a maximum value on an open interval. So just another example. And then we have a case here where we have closed interval. So we go back to the closed endpoints, but now the function may be defined as a piecewise function. This time we defined it to exclude the value of x equals 0 on the curve, but then we defined it elsewhere using this extra point. So we end up where the minimum had been. Now it's an actual open dot or a hole. So the function no longer has a minimum value on that interval. So these are just three examples to show that not every function is definitely going to have a min and a max on a given interval unless we can guarantee some information is true. And that's where we're kind of headed. We're going to look at a special theorem here in a few minutes. So for the first kind, relative extrema. So this is really more calculus based. This is we can do a lot more with relative extrema thanks to calculus. But a relative max or minimum, again, is a high or low point on a local section of a graph. We often refer to these as peaks or valleys for a graph. It's where we reach the top point or reach the bottom point. And we can find them much easier now that we know something about calculus. So we're going to do a little exploration here with these three functions and their graphs. So for these three, we're going to find the derivatives value for each of the following functions at their indicated relative extrema. So we have the graphs already. Now, we're not always going to have the graph because if you already know the graph, you can identify extrema just simply by looking at the function's curve. So it makes it a lot easier when you already have the graph. We will typically be doing it with just the function, but it's important for us to make these connections between what the equation says and what the graph actually shows us. So that's why we're going to start with both and try to hopefully make this connection. So for the first graph, we have a relative maximum. You guys can see the graph is super steep, really, really steep, and then it flattens out very quickly, and we reach a maximum, and then it takes off. So it starts to decrease after this. It just doesn't do it in a very quick manner, but it's still technically decreasing. So we reach a relative maximum up at this point, and they want to know what is the derivatives value at this point. So we're going to take the derivative of this function. Now, if you look at this guy, it looks like it's set up as a quotient, but if I were to distribute in the numerator, I get 9x squared minus 27. And now this has that form of a plus b over c, where I have multiple terms in the numerator, one term in the denominator. So this allows me to split and reduce this fraction. So I'm going to rewrite this guy as x squared over x cubed is 9x to the negative first minus 27x to the negative third. So when I split that, I can reduce any common variable factors and then rewrite it so that I can take the derivative with the power rule. So now if I take the derivative of this new form, I get negative 9x to the negative second plus 81x to the negative fourth. Or if I clean that up, I get negative 9 over x squared plus 81x to the fourth. Now, there are some more simplifications that I could do with that if I wanted to, but in this case, my job is just to figure out what the value of this derivative is at that point. So I'm going to plug 3 into this guy. So f prime of 3 would give me negative 9 over 9 plus 81 over 81, or negative 1 plus 1, so 0. So we're going to leave that there. As I go through these next two examples, though, I want you to try and brainstorm what the implications of this value at f prime of 3 equaling 0 really has for this graph. Think about everything that we've learned up to this point about the function f prime and what its output values represent in the context of a function's curve. So now let's take a look at this second guy. So I have f of x equals the absolute value of x, and we're going to look at the relative minimum, this turning point. Remember, this is one of those sharp turns because it's the absolute value graph at 0, 0. But before I do this, I'm going to redefine this guy. Remember that the absolute value function is really a piecewise. It is equal to the opposite of whatever we choose as our input when that input is less than 0, and it's equal to the actual input when x is greater than or equal to 0. So when I go to find f prime, the derivative of negative x is negative 1 when x is less than 0. But even though this function is continuous at x equals 0, because of the sharp turn, we cannot include 0 as a value of x in the domain of the derivative because the function is not differentiable at those sharp turns. So the derivative of x is just 1, but now that is only on the interval from x is greater than 0, no more equals. So now I have the derivative, but now our goal is to figure out the value of f prime at that point where we said it's not differentiable. So the issue with that becomes when I go to plug 0 into this derivative equation, all we can really say is that the derivative at 0 is actually undefined. And again, without revealing too much, still want you to brainstorm. Think about what that means in the context of the relationship between the function f prime and the graph of the original function f. So just think about those two as we do this last guy. All right, so for the third one, we have f of x equals sine of x. And this one actually has two relative extrema, at least on the portion of the graph that we're looking at. But remember, this is a cyclical graph or a periodic function. It repeats that wave pattern over and over again. So this function actually has an infinite number of relative maximum and an infinite number of minima as well. So, but for the 2 points that they gave us, we have f prime. Remember, the derivative of sine of x is cosine of x. So f prime at pi over 2 would be cosine at pi over 2. Remember to evaluate these trigs. We can sketch our little unit circle. Think of where this angle is. Pi over 2 rotates to 90 degrees, or the positive y-axis. So the x-coordinate there is 0. So that is the value of f prime at pi over 2. And then at 3 pi over 2, that is 270 degrees. So that is rotating to the negative y-axis, where x is still just 0. So both of these end up having a value of 0. So we evaluated all three of these problems. So we looked at the value of the derivative when or at the points where our function reaches either a relative minimum or maximum. And hopefully, now that you guys have been thinking a little bit about this, you've come to realize that the big connection here. So remember that the value of a derivative function at x equals c is the slope of the tangent line of the function f, or remember that is the same as saying our instantaneous rate of change of f. So when we see these points at these relative minimums or maximum, there are really only two ways that I can reach those points, and both of them revolve around the idea of changing direction. So a function must change direction from increasing to decreasing or decreasing to increasing to create one of these relative extrema. The only way that I can do that is one of two ways. We have a smooth turning point where we go from increasing to the turning point to decreasing, but that really means that we are going from positive slope for the tangent line to negative slopes of the tangent line. And if that occurs naturally, the only way that we naturally go from positive to negative numbers is if we pass by 0. So what we're really saying is at these smooth turning points, we have a tangent line or an instantaneous rate of change of 0. The other option, the other possibility of changing directions is to do it unnaturally. Instead of going from positive to 0 to negative, we go from negative to a violent and drastic change into positive slopes, and we do that at a sharp turn. That is where it's unnatural. We didn't come to a complete stop. So that is where we have undefined values for the derivative. That undefined value represents a place where we have reached that drastic or sharp change in directions. So what that does is that helps us make a connection between the graph of f and the value of f prime. And it does it through points called critical numbers. So when our goal is to try and locate relative extrema of a function, we're first going to try and find all values of x where extrema could possibly exist. So a critical number is a candidate for a relative extremum. So basically what that means is they occur on a graph anywhere that f prime is equal to 0 or any value of x where f prime is undefined. And again, that means that f of x is not differentiable there. So remember that whenever f prime is undefined, there's really only three ways that can happen. One, it's because f is discontinuous at that value of x. And if that's the case, we would really know that already, or we'd be able to kind of recognize that there's a chance of that. So that would be like where f has holes. So that would be like a piecewise or a rational function, or where we have vertical asymptotes. Again, probably one of those guys, or some kind of jump or break discontinuity. So again, piecewise. So the discontinuity issue is one that can kind of sort itself out relatively easily. The other two are a little bit harder, and we have to do some investigating for. But one case is that vertical tangent. So think of x to the 1/3 power, that graph I've shown you in the past. The graph goes vertical just for a split single value of x, and then continues on with positive but less steep slopes. But then the third option is the one we've already talked about, and that is the sharp turn option. So again, whether it's the bird graphs or absolute value functions, those are the ones that we are looking for. Vertical tangents are places where f prime is undefined, but the big difference here is this graph is always increasing. So while it is undefined at the vertical tangent, it actually never changes directions, and that's an important piece, okay? So for a critical number to eventually turn into a relative extrema, we have to be able to show that one of these two conditions are true, so it is a critical number, but then also we have a change in direction. That's the harder part. That's what we're going to do later on in this unit. But for right now, our first step is identifying where these critical values are or critical numbers are, because that is the important first step. That limits it, and we know that there's at least a chance that those values are going to turn into these turning points or relative extrema. So relative extrema for any function must occur at a critical number. That is a really big important rule. This is just how we kind of narrow down the process. Instead of having to think of all possible values in the domain of our derivative function, we can really limit our scope to just focus on a couple of values that we know have the potential to be turning points. So if we can identify those, then we'll use our derivative to help us sort out which ones actually are extrema or not. Okay, so critical numbers is the first key piece to this puzzle of gathering information about a function's graph. So now we're going to take that and kind of help us talk about the other kind of extrema. So the first important theorem here for us is the extreme value theorem, and it says that if f is continuous on a closed interval, so those first two pieces to this theorem are super important. So first off, the function has to be continuous. So if you think back to those three graphs that we looked at the beginning, the fact that the function is continuous on this interval means in the middle of it, there can't ever be points where there are vertical asymptotes, holes, or jumps in the graph. So that eliminates a lot of the nonsense that we have to sometimes worry about going on a function's graph. So that part's important. The second part is that it is a closed interval. So because it's a closed interval, that eliminates one of the examples from the graphs earlier where we had open holes at the end of the intervals, which eliminated there being a maximum on this right side. So what we're saying is we are guaranteeing right off the bat that if we meet those two conditions, then f is guaranteed to have both a minimum and a maximum on this given interval. So this is a way of proving that a function will definitely have an absolute min and an absolute max on an interval, as long as we know for sure it's continuous and we're given a closed interval. So really, as far as proving the conditions to use this guy, the closed interval part is going to be kind of given to us. They have to tell us what that interval is. So as long as it's closed, that part gets checked off. The continuity issue is something that we will have to do some work, or at least discuss in verifying that that condition passes. So as long as that works, then we have a way now that we can prove that there are extrema somewhere in this interval. So our process. So if we want to identify the absolute extrema for a continuous function f on a closed interval a to b, then we are trying to find where the absolute largest and smallest values of y occur. There are only ever 3 candidates for where these absolute extrema can occur, either at our endpoints a or b, or any critical numbers that exist in the interval. Because again, a critical number is a candidate for a relative extrema. So if the conditions are met, a critical number can turn into a relative extrema. So again, the idea or the possibilities here is we could have a graph that's similar to the one that we saw earlier, where our maximum ends up being one of the endpoints and a local min is inside or in the middle. So that is our absolute min inside. Or it could be kind of the other way around, where our minimum occurs at one of the endpoints, and then our maximum occurs at a relative extrema in the middle. Or it could just be that we don't have any turning points in between, and we just have a absolute min and max at both of our endpoints. But as long as that extreme value theorem applies and the function is continuous on that interval, and it's a closed interval, we know for sure that there's a min or max in there. So it's really either going to be at the ends or at one of our turning points in the middle. So the steps to guarantee or find these values, first we're going to identify any critical numbers that f has. So that is, again, where f prime equals 0 or is undefined within the given interval. Now, we don't check for critical numbers at our endpoints because, remember, the idea of slope or instantaneous rate of change and endpoints doesn't really work out because I can't take the limit of that secant line slope at an endpoint. I can't do it from both directions because one side would be outside of the interval. So whenever we're talking about differentiability, we switch from closed to open intervals. Then after I've got those list of x values, again, those are candidates for these middle points. Okay, so we're going to check those. But then we also have to consider the endpoints. And then we're just going to look at the y values or the values of the function at all of those possible places. And then it's just a matter of picking out what are the biggest, what are the smallest values. So it's a pretty easy 3-step process. So let's dive in and try one of these guys. So for this one, we want to find extrema. And again, it doesn't necessarily have to say it, but when I say extrema on an interval, that those two pieces, without directly saying it, implies that we are talking about absolute extrema. Okay? So again, it could come out and directly say, find the absolute extrema on this interval, or it can be phrased this way. This is typically how it's going to be expressed. So the fact that I'm giving you an interval is what's kind of implying that it is the absolute extrema version that we're looking for. So step 1, we're going to find our critical numbers. So that requires us to figure out the equation for f prime. So f prime of x is derivative of 3x to the 4th. That would be 12x cubed, minus derivative of 4x cubed would be 12x squared. So our original function f is a polynomial. It's a quartic, 4th degree. So because it's a polynomial, we know 2 things. First off, the domain of f is all reals. Because it's a polynomial, we know that f is continuous everywhere. And because it's a polynomial, we know that it is differentiable everywhere. So those 3 things makes this a really easy problem. So domain being all reals, we know that there's no continuity issues with our interval. So the extreme value theorem applies. It's a closed interval. So we know for sure that there is an absolute min and max that we can find here. And then the differentiable issue means that when I go to find my critical numbers, I don't have to worry about the undefined option. It's differentiable everywhere. The function always has a slope at every value of x in the domain. So I only have to worry about setting the derivative equal to 0 and finding those values of x. So if you can't guarantee that the original function is differentiable everywhere, then we do have to explore that option. But in this case, we end up with a polynomial equation. We can solve this by factoring out a GCF. Leaves me with 12x squared times x minus 1 equals 0. So then this guy produces a solution of x equals 0, and x minus 1 produces positive 1. So those are my critical numbers. Those are the values of x that if the function has a relative min or max, they must occur at either 0 or 1. So then we just check, do these fall in our interval? Sometimes we'll have extra critical numbers outside of our intervals, so we don't want to test those guys. But 0 and 1 are both within this interval from -1 to 2. So now we just are going to make a little chart, and we are going to we're going to kind of do steps 2 and 3 here. We're going to actually, let me get rid of that. Leave that alone for right now. So step 2, we are going to find the value of f at all of these values of x. So it's nice to set up your table in order. So your endpoints will be the first and last, and then our critical numbers in between. So 0, 1, and then 2. So again, these are my critical numbers, and then this is our endpoints. Okay? So now it's just a matter of evaluating f at all 4 of these values. So this is just some plug and chug stuff. So plugging -1 in there will give me, remember, a negative raised to a even power creates a positive. So this would give me 3 minus a negative raised to an odd power creates a negative. So this is actually going to switch to a +4. So I get 7 for that guy. 0 going in is easy. It's going to make 0. 1, I get 3 minus 4, or -1. And then 2 going in, I get 16 times 3 is 48. Minus 2 cubed is 8 times 4 is 32. So 16. So then it's just a matter of step 3 would then be identifying out of those values of y, which are the biggest and smallest. So out of all of those, -1 is the smallest y value, and positive 16 is the largest. So then I can say that we have an absolute minimum on this interval at the point 1, -1, and we have an absolute maximum at the point 2, 16. Now you do have to be very careful with the way that we present our answers. Sometimes we may be interested in just the y-coordinate. Other times we may be interested in where on the graph those extrema occur. So sometimes we may want to know the actual coordinate. So depending on what software you're working in, it really will dictate how exactly we present this. If it's asking for coordinates, then we give both. But again, sometimes it may just want the y-coordinate. So we could just be answering, what is the absolute minimum value of the function on the interval? Well, that would be -1. What's the absolute maximum? That would be 16. So how we present our answer is really a case-by-case basis, and what exactly software or format it's asking for. But the process will not change. Critical numbers, use those in the endpoints to test, see which y values are biggest. Those are our extrema. All right, let's take a look at another example. So same process, different function though, and this one we're going to take a look at on the interval from -1 to 3. So again, step 1, we need to identify our critical numbers. So to find critical numbers, we need to know the equation for f prime. So f prime of x, in this case, derivative of 2x would be 2. Fractional exponents, remember this is still power rule, but when I bring 2/3 down and multiply by 3, I'm going to get 2 as our new coefficient. And then 2/3 minus 1, again, -1 whole is like 3/3. So we get -1/3 for our new power. So then if I clean that up, I get 2 minus 2 over x to the 1/3 as our derivative. Now, if we go back to the original function a little bit and think about some of the conditions here. So as far as domain goes, so 2x, that term is linear, it's polynomial, no issues there. But our second term there with the fractional exponent, that's the one that can cause some issues. So it's really all about the denominator in the fraction. If the denominator is even, then that's like trying to take a even root or a square root or a fourth root. That's where we run into issues with negative values. So in this case, because it's an odd root, so this is like taking x squared raised to the 1/3 power, or the cube root of x squared. So when I plug in any number, the square will make it positive, and then the cube root is no issue. So the domain for this original function is still all real numbers, which means we don't have any discontinuities. There are no holes. We're not jumping over anything. Again, the jumps and breaks don't occur unless we have a piecewise function. But we know that there's no asymptotes or holes because that would have an impact on the domain. So that means that the function is continuous everywhere. So because of that, we know the extreme value theorem applies, and we can find extrema, absolute mins, and maxes in the interval somewhere. However, for differentiability, differentiability relates to the derivative function. So our previous function was differentiable everywhere, and if you notice, that is for two reasons. We talked about it being so because it's a polynomial, but it's also true because the derivative has a domain of all reals. The domain of this cubic is also all reals because the derivative of a strictly polynomial function is another polynomial. But it's all about the domain of that derivative. If it is all reals, then the original guy is differentiable everywhere. In this case, we don't have that same thing. If we think about the domain of f prime of x, well, that is all real numbers except for 0. X cannot equal 0 for this derivative because that would make the denominator 0. It would make f prime undefined. Well, that's one of the conditions for being a critical number. So yes, I'm going to set this guy equal to 0 and solve, but this is actually already one of our critical numbers. So we need to make sure that we don't forget about this guy. 0 will be one of our critical numbers because it is where the derivative is undefined or where the original function is not differentiable. So it could be the case that it turns out to be a sharp turn. We won't know right off the bat until we do a little bit more work, okay? So we have the where f prime is undefined. Now we're going to set it equal to 0 and solve. So I'm going to move the fraction over. So 2 equals 2 over x to the 1/3. This is really a proportion, so I'm just going to exchange on the diagonals. I get an equivalent form, just a lot faster. So we end up with x to the 1/3 equals 2 over 2, or 1. And then to get rid of a cube root or a fractional exponent, we just raise both sides to its reciprocal. So we're going to cube both sides. So we get x equals 1 cubed, or 1. So our critical numbers in this case are x equals 0 and 1. 0 is where f prime is undefined. It's a place where the original function could either have a vertical tangent or a sharp turn. And then 1 is where the derivative equals 0. So with 0 slope, there's two possibilities. It could be a turning point like this guy, but it can also be a flat spot on the graph. Just like undefined slope values of derivatives, there are two cases. Same thing with 0 slope. Sometimes it's where we we have turning points or we change directions. Other times it's just where the graph goes flat for a second. So you can kind of think of this as like the inverse of the vertical tangent. So we won't, again, know exactly what's going on until we do some stuff in the next section. But for right now, these are critical numbers. We know we have to check these guys on our chart. So let's set this up. And again, 0 and 1, both of those fall in the interval, so we will include both of them. So -1, 0, 1, and 3. Okay. Now, as far as the 0 thing goes, for right now, because we're not necessarily looking for relative extrema, we just want to know what's the biggest and smallest y value. We actually don't care whether this is a vertical tangent or a turning or sharp turn just yet. We just want to know what's the highest and the lowest y values anywhere on the graph. So that explanation or that analysis is, we're going to put that on the back burner till we get to the next section. So for right now, we're going to go through, put all these guys in. So we get -2 minus, so this is a little bit complicated, so think of it in steps. I'm going to put my x value in, square it, then take the cube root of that result. So negative 1 squared is 1, cube root of 1 is 1, times 3. So we get negative 2 minus 3 is negative 5. 0 going in for both is just 0. That one's easy. Positive 1 going in would be 2. And then 1 to any power is just 1. So 2 minus 3 is negative 1. And then 3, this is going to be the tricky one. Okay, we're going to do our best to estimate here. I'm going to walk you through some mental estimation. So 2 times 3 is 6, minus 3 squared is 9, cube root of 9. Well, we don't really have an exact value of that without a calculator, but I'm going to show you how we can do our best to estimate this guy. Okay, so what I do know for sure is cube root of 9 is going to be slightly more than the cube root of 8, which I know is 2. So if cube root of 8 is 2, cube root of 9, I could estimate that it's like 2 point something, 2.1-ish, something like that. And while I don't need to know the exact value, what I do know is that if I take 3 and multiply it by something that is bigger than 2, that's going to make this guy bigger than 6. So if I take 6 minus something slightly larger than 6, I know that this is going to be a negative number. It's not going to be a large negative number. It's not even going to be more than negative 1. I know that. But I do know that it's definitely going to be negative. And as far as what we are looking to do here, we are trying to analyze what is the smallest and largest values on this interval. So no matter what this negative number comes out to be, it's not going to be a smaller value than negative 5. So I know that this is my minimum. The fact that this is a negative value also tells me that 0 is actually going to be the largest y value used anywhere on this graph. So while I can estimate this to some degree of accuracy, I can get it to a point where I don't need to know the exact value because I can use my logic and reasoning to determine that this value is actually not of any importance to us. So then I can say now that we have an absolute minimum at the point -1, -5, and absolute maximum at 0, 0. And again, if they asked for what is the absolute min, then they may just want the y coordinate or the y value. So that would be min of -5, maximum of 0. All right, so let's take a look at our next example here. So for this one, we're going to find the extrema of f of x equals 2 sine of x minus cosine of 2x on the interval from 0 to 2 pi. So again, we have an interval, so we're looking for absolute extrema here. So first step, we're going to find these critical numbers. Now, again, one helpful tip here sometimes is thinking about the domain and differentiability and continuity of this original function. So if you guys remember, sine and cosine independently each have a domain of all reals. So when I create a composition by combining those two through addition or subtraction, that domain is not going to change, still all reals. If you also remember, these functions are well behaved. There are no holes, asymptotes, break discontinuities, nothing like that. So this function is continuous on its entire domain, which is everywhere, all reals. And there are no sharp turns that naturally occur or vertical tangents with sines and cosines. Or another way of thinking about that is we know that the derivative of f of x, or excuse me, of sine of x and cosine just turn back into sines and cosines. So in this case, our derivative would turn into 2 cosine of x. Now for cosine of 2x, off here to the side, we need to do a chain rule. U would be 2x. U prime would just be 2. Oh, excuse me. Said 2 and then wrote 2x. Would just be 2. So then when I make this cosine of u, its derivative turns into negative sine of u times u prime, or negative 2. I'm going to move the u prime out in front. Negative 2 sine of 2x. Oh, actually, sorry. This is supposed to be positive. So again, this was negative cosine of 2x to start. So if this is negative cosine of u, that'll actually switch to being positive 2. Okay. Now, so for our derivative, again, because it's just made up of cosines and sines, we know the domain of this guy, this equation, again, is all reals. And again, because that's the derivative function, when that domain means it's all real. So just reinforcing the idea that this function is differentiable everywhere. So again, and that kind of goes back to the idea of the original not having any vertical tangents or sharp turns, like we said earlier. The sines and cosines don't really produce that kind of stuff. So again, that means I only have to worry about figuring out where the derivative is equal to 0 and not necessarily thinking about where it's undefined. So let's do that. So if I set my derivative equal to 0 and try to solve, then we run into a separate issue. So if you think back to pre-calculus, when you guys were first learning about trigonometric equations, one of the rules was when we have different function types mixed together in the same equation, we have to make sure that their arguments are identical. So when these trig functions have different arguments, they don't interact the same way, because when I plug in x equals pi over 2 into the cosine, it's taking me to a different place on the unit circle than when I double that and it takes me to 2 pi over 2, or pi. So we want these arguments to be the same before I actually try and do any manipulation to solve the equation. So in order to do that, we actually need to use one of our trigonometric identities, and in particular, the double angle formula. So the double angle formula says that the sine of 2u is actually equal to 2 times the sine of u times the cosine of u. Or basically, when I want to reduce the argument of a sine function, we cut it in half and give each half to a sine function and a cosine function, but then we double their product. So you can kind of think of it like the 2 is coming out, that becomes the new coefficient, and then we have to have a product of those two functions. So lots of different ways to help you memorize it, but this is the rule. So notice that I can go from a 2x as an argument down to just 1x in each of these, which is what I need to do here. It's much easier to start with a big argument and cut it down and reduce it than it is to go the other way. So that's what I'm going to do. I'm going to replace this sine of 2x with the identity, but because there's already a coefficient of 2 in front of here, it just means it's going to get multiplied by what's already there. So this will become 4 sine of x cosine of x equals 0. Now we can solve by any means. A lot of times when I've got sines and cosines mixed together, we tend to end up factoring that. And in this case, if you notice the structure, I do have a common factor of 2 cosine x in both of these guys. So that leaves me with 1 plus 2 sine of x equals 0. So now we set each factor equal to 0 and we solve. So we got 2 cosine of x equal to 0. I can divide by 2 to get rid of the coefficient. So I'm really left figuring out in our given interval what angles have an x coordinate, because it's cosine of 0. Well, that would be up at the positive y-axis and then down at the bottom on the negative side. So that would produce solutions of x equals pi over 2 and 3 pi over 2. Well, that was a bad 2. So those are our first two critical numbers. Now we got to set the other factor equal to 0 and solve as well. So if I subtract 1, divide by 2, we end up getting sine of x equals negative 1/2. Now I need to brainstorm on my unit circle. So sine is the y coordinate. Negative 1/2 means I'm down in the third and fourth quadrants. 1/2, though, if you think back to the reference angles in the first quadrant, 1/2 is the smaller of the coordinates. So that means my y coordinate is smaller than my x. So this is a short wide triangle. So big x coordinate, small y. So that means that's the low-lying angle of pi over 6. But it can't be positive pi over 6 because that wouldn't have a y coordinate of positive 1/2. So it has to be the third and fourth quadrant multiples of pi over 6. So that will produce 7 pi over 6 and 11 pi over 6. Those are the third and fourth quadrant multiples for pi over 6. So now I have my 4 critical numbers in this case. So remember, our next step now will be just testing out what are the y values at all the critical numbers. And again, we still check our endpoints. So, whoops. Now we do want to go in order. Actually, that's right. So 0 pi over 2, then 7 pi over 6 would be next. And then 3 pi over 2 would be next after that. Then 11 pi over 6, and then 2 pi. Now, it's not common for all of these problems to have this many critical numbers, but you do see it quite often with trig because it's cyclical, that means those y values are going to repeat themselves a lot of times, not always the same intervals or whatever, but it is a common trend with trig functions to have a lot more critical numbers or a lot more places where f prime is 0 or undefined because of that cyclical nature with the period of these functions. So that does actually help us though, because remember that when I evaluate sine or cosine, sine or cosine at 0 and 2 pi, they are the same angle. They exist in the same place on the unit circle. They have the same coordinates, so it's one less thing that I have to actually evaluate. So when I plug 0 in here, I get 2 sine of 0, which is 0, minus cosine of 0, which is 1. So I get -1 for that. And that tells me I also know that 2 pi has that same value of -1 as well. Then for pi over 2, so I'm going to write some of these out, make it a little bit easier. So 2 sine of pi over 2, remember the y-coordinate of pi over 2 was 1. So 2 times 1 is 2. And then minus cosine of, now remember, these angles are going in for x. So with this cosine function, we have to double them before we evaluate using the unit circle. So pi over 2 times 2 would be pi. So cosine at pi would be -1. So minus -1 will produce +3. All right, now the next one, sine of pi over 6. So 2 sine of 7 pi over 6. Again, we know what those are because we just did that not too long ago. So that would be -1/2 times 2, or -1. And then minus cosine. When I double this guy, I get 7 pi over 3. 7 pi over 3 is more than one revolution. That is 2 whole pi, or 6 pi over 3, plus one more. So that would be at the pi over 3 in the first quadrant. The x-coordinate there, remember that's a tall, skinny triangle. So the x-coordinate is small. So that is -1/2. Or excuse me, -1/2. So we end up with -3/2, or -1.5. Okay, so then for 3 pi over 2, we have 2 sine of 3 pi over 2. Y-coordinate 3 pi over 2 down at the bottom is -1. So this is -2 minus cosine at 3 pi over 2 times 2 becomes 3 pi. And remember, 3 pi is one full revolution plus another half. So the x-coordinate there is -1. So this becomes -2 plus 1, or -1 as well. And then for our last one, 11 pi over 6. So we know that the sine at 11 pi over 6 is -1/2. So times 2 gives me -1. Minus, then we have another one of these where I have to double this. So this actually becomes cosine of 11 pi over 3. Well, 6 pi over 3 is one full revolution. So then I need 5 pi over 3 more, which puts me back down in that fourth quadrant. And in the fourth quadrant, again, it's a tall, skinny triangle again. So it's the same size x-coordinate as pi over 3. But again, in the fourth quadrant, cosine is our x. It's still positive. So it actually is the exact same coordinate as before. So we're going to do -1 minus 1/2 again, or -3/2. So those are all of my y coordinates. So again, now we just have to sort them out. Out of all of these guys, we actually have 2 places where we reach an absolute minimum. So 2 points, or 2 different x coordinates, produce that same minimum value. And then for our absolute maximum, it is this one value at pi over 2, 3. So just because I kind of ran out of room, I'm just going to label these. There are my maxes, or excuse me, there's our max, and then these are our absolute minimums. All right, so our last part of this video is all about 2 concepts that are actually really closely related to each other. But it's about the idea of trying to be able to prove that a function has a particular slope inside of a given interval. So remember, slope of a curve or slope of a function or instantaneous rate of a function all has to do with the value of a derivative of a function. So essentially what we're trying to do here is prove that the derivative will be equal to some particular value uh, within a particular interval of x values. So if you think back, we've talked about other theorems about trying to prove that things exist If you think back to the intermediate value theorem is a way of proving that if a function is continuous on a given interval, then every y value between their two endpoints y values have to be used. And it's a way that we can guarantee that particular y values are guaranteed to exist within a given interval. This is along the same lines, but it has to do with the slope of a function. Or in other words, we can kind of think of it almost like an intermediate value theorem for the derivative function, but it's all based on values of the original. So the formal definition of mean value theorem says that if f is continuous on a closed interval a to b, so again, continuity plays a really big important role with a lot of this stuff. Because it's continuous, we can guarantee that there's no weird stuff going on, no holes, jumps, asymptotes, none of that stuff. But it also has to be differentiable on the open interval. So again, that's important too. That means that there can't be any vertical tangents, there can't be any sharp turns within that interval, so that there is always a real world value slope, a real number value slope at every point within that interval. So if that's true, then there exists some number c, so some x coordinate in the interval such that the value of the derivative is equal to f of b minus f of a all over b minus a. Or another way of saying that, f prime of c, remember that is like saying the slope of the tangent line, and f of b minus f of a over b minus a, if you remember back to the beginning of our discussion on rates of change, that is actually the slope of the secant line. So that's essentially what this mean value theorem is guaranteeing. So not only just any secant line, but it's the secant line through your endpoints. Or another way of saying that is, at some point, the instantaneous rate of change at some moment in time in the middle of the interval must be equal to the average rate of change on the interval from A to B. That's essentially what this is saying, and this diagram does a pretty good job of showing it. So my endpoints are here at x equals a, x equals b. No matter how those two are graphed, they will always create some kind of secant line, and at some point in the interval, there has to be at least one point, sometimes there's more than one, but at least one place where the tangent line has the exact same rate of change or exact same slope as the secant line through the endpoints. Or a simple, easy, real-world example to think about this is, suppose that you travel 100 miles in 2 hours. Well, that would be an average rate of change of 50 miles per hour. It is impossible, because of the mean value theorem, it is impossible for someone to travel this distance in that amount of time and never go the speed of 50 miles per hour. It's impossible. Now, obviously, a vehicle can't go automatically 50 miles per hour the entire time. There's going to be fluctuations in the speed of that car along the trip, but it would be impossible for us to always travel below 50 miles per hour and still complete this trip in 2 hours. So that is what this is kind of saying. It's a way of guaranteeing that the instantaneous rate of change will always match the average rate of change across the interval at some point, which is really helpful to us in certain situations, certain applications. So to actually utilize this and help us answer some questions, it's basically just trying to figure out what is that average rate of change that I have to match. So given f of x equals 5 minus 4 over x, we want to find all values c in the open interval 1 to 4, such that the derivative's value matches the secant line slope. Okay? So the first part of this is, what is our average rate of change? So what is the slope of the secant line, or the average rate of change across the interval? So we actually need to evaluate f of 4 minus f of 1 over 4 minus 1. So f of 4, if I plug 4 in, I get 5 minus 4 over 4. So 5 minus 1 is 4. Minus, if I plug 1 in, I get 5 minus 4 over 1, which is also 1, 5 minus 4. And then over 4 minus 1, so that just comes out to be 1. So essentially what this is saying is, again, I don't even need to see the entire graph. I know that when x is 1, y is 1. When x is 4, y is 4. no matter what the curve looks like throughout that process, I know that there is 2 points that this curve passes through. So I know that the secant line would have a slope of +1. So what I want to say, or what I need to be able to prove, is that at some point the curve has an instantaneous rate of change of exactly that same value, so exactly 1. So if that's the case, we need to be able to find the derivative and set it equal to that number to find that value of x where this occurs. So if I take the derivative of this guy, the derivative of 5 is 0. -4 over x is really -4x to the negative first power. So I get 4x to the negative second, or 4 over x squared. So I can now set that equal to 1. Again, this is f prime. This is the slope of the secant line. I want to know, where do these two equal one another? Or in other words, this represents the slope of the tangent line. This is the slope of the secant line. So I'm looking for that value of x that makes this true. So if I solve this, exchange on the diagonals, I get 4 equals x squared, or x equals plus or minus 2. But we're only looking for it in the interval from 1 to 4. So we're only going to take +2 as the value of c that we are looking for. So what that means is that if I were to actually graph this curve and look at the graph of the tangent line, I know that at x equals 2, its slope has to match the exact slope of this secant line. So that the curve looks something like this guy, and at x equals 2, we would have a tangent line that is parallel to the secant line. And that's the big idea behind this mean value theorem. Again, it's a way of guaranteeing that the slope of the tangent line is equal to a particular value somewhere in this interval. Or for a more real-world example, suppose 2 stationary patrol cars equipped with radar equipment are 5 miles apart on a highway. So here's my highway. Here's cop car A. And here's cop car B. Not sure why they're different sizes. Don't judge me. But they are 5 miles apart, okay? And a truck passes the first patrol car. The speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. So it was 55 here, 50 here. And again, the truck traveled that 5 miles in 4 minutes. So 4 minutes later, its its speed is tracked again. But we want to be able to prove that the truck must have exceeded the speed limit of 55 miles per hour at some time during the 4 minutes. So what this is doing, if your local police officers actually know how to do some calculus, they can actually track this information and prove that these cars had to have been speeding. So first off, if we go back to the definition requires these functions to be continuous and differentiable on the open intervals. And I apologize, I did skip over that part in this first example. We can do it real quick. This function, its domain is all real numbers except x can't equal 0. 0 is not in the interval given. So we know that these rational functions, they don't have any holes or asymptotes because in the interval, there is no vertical asymptote. This guy does have one at x equals 0, but that's not a part of this. And at as far as differentiability goes, if we look at the domain of our derivative function, it has actually the exact same domain. The only value that x can't equal is 0. So that would be the only place it's not differentiable. And again, the first guy had a vertical asymptote there. So because of that, the mean value theorem would apply. It's continuous and differentiable everywhere in this specific interval. Now, interpreting continuity and differentiability in terms of this real-world problem, well, we have to think about what's going on here in our inputs and outputs. So in this case, we are looking at an input of time measured in minutes, and the output would kind of be the truck's position, which would be measured in miles. So as far as continuity goes, as long as at every moment in time from 0 to 4 minutes, the truck had a position, then we would say it's continuous. So unless the truck magically disappeared in between passing those two trucks, which we wouldn't assume to be true, that would be the only way that this function would not be continuous. So it's safe for us to assume the car didn't magically disappear. So that checks out. For differentiability, we would just have to be able to guarantee that we can measure the truck's speed at any given moment in time. And again, even if the truck stopped, it still has a speed. It would just have a speed of 0. So because of the real life context here, we can guarantee that the differentiability condition passes as well. So because that passes, the mean value theorem applies. So what that's saying is this information implies an average rate of change. If I assume that all this stuff kind of starts when we pass the first truck, that would be after 0 minutes, I'm 0 miles from the first police officer. After 4 minutes, I am now 5 miles past that first police officer. So these kind of act as our 2 points, or the endpoints on our graph. So from 0, 0 to 4, 5. So now I would want to be able to prove that at some point the truck's instantaneous rate of change, so what the speedometer on their dashboard read, must have been higher than 55 miles per hour. So what we can do is we can use the average rate of change to prove that at some point, if that average rate of change is exceeding 55, then the instantaneous rate of change must have equaled that value at some point. So let's do that. So we're going to find the slope of our secant line, or our average rate of change. So our secant y minus our first over our second x value minus our first. So this is 5 miles in 4 minutes, which shouldn't have been too big of a surprise because we already knew that ratio. But now we need to convert this into miles per hour. So I don't want minutes down here anymore. I want hours down here. Hours is a larger unit, so we need to break that up into smaller pieces. And we do that by multiplying by an equivalent ratio. So 60 minutes is equivalent to 1 hour. Doing that will eliminate the units of minutes. So we get 300 miles every 4 hours, or 75 miles per 1 hour. So this information is saying that the average speed of this truck across that interval had to have been 75 miles per hour. That means, based on the mean value theorem, there is no way that you could have traveled 5 miles in 4 minutes and never reached a speed of 75 miles per hour. So even if we were to travel, even if the car was magically able to go from stopped to instantaneously traveling at 74 miles per hour, if I do that for 4 minutes, it's not going to equate to 5 miles. It's going to be slightly less than that. And that's where the issue comes from. This is like, if you do that, it's like 4.9 something miles. So the only way that I can actually travel 5 miles in 4 minutes is if I at least travel 75 miles per hour one time. I have to get up to there. Most likely I'm traveling above that speed for a large portion of this trip. But there is a guaranteed time at some point in between here where the instantaneous rate of change is at least 75 miles per hour. That is what the mean value theorem guarantees. That's why if you ever see a speed trap set up where there are 2 cops, or sometimes you'll see some surveyors taking data where you travel over these wires, they're actually tracking average speeds on roads, and that's what the computers are doing. They're tracking that average rate of change, and we can use that to guarantee instantaneous rates of change between those 2 points. So our last topic is actually, this guy is just a specific case of the mean value theorem. So when we understand how to check for and apply the mean value theorem, we can actually use an extension of it to try and prove the existence of an extrema. So and in this case, we're talking about a relative extrema. So that is one of those turning points, whether it's a smooth turning point or one of these sharp turning points. But so what we're essentially doing, we're essentially going to take what we know about the mean value theorem and critical numbers and kind of combine them to prove the existence of a relative extrema. So again, what mean value theorem said is if the function is continuous and differentiable on an interval, then whatever the average rate of change through the endpoints is equal to, so the slope of the secant line, again, it guarantees that somewhere in that interval, the tangent line will match its slope and be parallel to the secant line through the endpoints. Well, if we think about critical numbers, we know that critical numbers exist where f prime either equals 0 or is undefined. And specifically, this equals 0 part is what we're concerned with. It's harder to do. We can't really do it with undefined because, again, mean value theorem says that we need the function to be differentiable on the interval, and it's not differentiable at these sharp turns. So if we focus on the where f prime equals 0 condition, we can actually create this new rule. All right, so let's try to build this new rule. So this new rule is called Rolle's theorem. It's named after the guy who worked it out. But again, the mean value theorem says that if we know a function is continuous on an interval a to b, then we know that there's some value of x in the interval where the slope of the tangent will be equal to the slope of the secant. Again, that's the main driving concept behind this. But now what we're going to do is we're going to do something specific to that secant line. So again, the secant line's passing through the endpoints, but now we want to consider an interval where both endpoints are equal to each other in their y values. So we have to kind of consider or think about that case. So if I had 2 points, it really doesn't matter where A and B are, but if I know that f of A is equal to f of B, now I have to try and consider what implications that has as far as the tangent line. So if we have a function like that, then we know that the secant line has to pass through both endpoints. But remember, the slope of the secant line is equal to f of b minus f of a over b minus a. And if these guys are equal to each other, well, then the slope of the secant is actually going to be 0. And if the mean value theorem says, as long as the function is continuous between the endpoints, then at some point that tangent line will have slope equal to the secant line. So what that's saying is at some point between these guys, the slope of the tangent must be equal to 0 at some point. So that's what we're talking about. And now I just realized that I actually had some blank space to write that down here. So what we're saying is by this extra little condition, I now know that the slope of the secant line has to be equal to 0, which means by the mean value theorem, we can prove that at some point in the interval, the slope of the tangent line must be equal to 0. So what does that look like? Well, there are 3 general representations or cases where all of this can be true. So I'm just going to sketch out my secant line for all 3 of them. So we have to kind of consider, well, how could I possibly get to those endpoints and have the slope be equal to 0 through the endpoints? Well, one possibility is if I start at this endpoint, I can go up from there and come back down. So if that was the case, then we do, in fact, have a point in between where the slope of the tangent is also equal to 0. Another possibility is we start going down from that first endpoint, and then we turn back up to get back up to that same y. In that case, we still have a place where the slope of the tangent equals 0. It's just occurring at a minimum value. And then the third case, this is kind of a trivial case is how it's referred to, is the actual function could just be a constant line. So it could just be the line y equals f of a or whatever f of a or f of b are equal to. And if that were the case, then the conditions still work out and we still have the final result. The only thing about this is it's not really all that special because everywhere on that graph between the endpoints would have a slope of 0. So that's not all that interesting. So we don't really necessarily concern ourselves with this because we would know that the derivative looks like this simply by the fact that the original function would have to be a constant function. So there's nothing really exciting there. We don't do much analysis of constant functions because they're kind of boring. So what we do know, though, or what we can now do is say that we can prove for sure that as long as the function is continuous and differentiable between that interval and the endpoints equal each other, then the secant line will have a slope of 0, which therefore means somewhere in the interval the tangent line equals or has a slope of 0. which, because the graph is continuous and differentiable in the interval, we have proven that there is a turning point somewhere in that interval. So that is pretty important here. We know for sure that there is at least one turning point, or relative extrema, in between A and B inside of that interval. And it actually could be the case that there are a whole bunch. Since we don't really need this trivial case graph, we could have a function that has a whole bunch of twists and turns in between. And remember, Rolle's theorem and mean value theorem, they don't limit it to just one possible value where all this exists. It's saying there's at least one place where this is guaranteed to occur. So that's the really big case here. So Rolle's theorem is really still doing mean value theorem. It's just, instead of it being any kind of slope, it's really restricted to zero slope. And because it's zero slope, that is a way for us to prove that a relative min or max must occur somewhere within that interval. And those are really important points for us. So then we can go and actually try to solve and figure out where are those relative extrema. All right, so if we try to put all this together, let's write out what we can prove here with Rolle's theorem. So again, we still have the same conditions from mean value. So I'm going to do this in kind of shorthand. But so for f, we need it to be continuous on our closed interval a to b, and pretend that's a square bracket, and differentiable on the open interval a to b. So again, those two things still have to be true. No jumps and breaks or holes, no sharp turns or vertical tangents, because again, those don't really match up with what we're trying to do here. So if that is true, and we have to add in the extra case here, that f of a equals f of b, that's the way that we guarantee that we have zero slope, then according to Rolle's, because I forgot if, then by Rolle's theorem, there exists at least one value of C in the interval a to b where a relative extrema must exist. So that's what we learned, but again, the in-between, the proof, is what we talked about up here. If those first three conditions are true, then the secant line slope has to equal 0, which by mean value guarantees the slope of the tangent must equal 0. And because we eliminated all of these extra possible scenarios of the sharp turns or the vertical tangents and all that extra stuff with the differentiability condition, we are guaranteed that there is a relative min or max. There is no way to start from a y value and end up with the same one without changing directions in between, or again, that trivial case, you could have stayed constant the whole time, which still would create that slope of the tangent line being 0 and still have a relative min or max. It's just not exciting because they're all that same value. So that is our big takeaway here. So now if we take a look at a couple of examples here, so now we're actually going to try and find these. So we're going to use the zeros of f of x equals x squared minus 3x plus 2 to show that f prime of x equals 0 at some point between the two zeros. So this time, instead of actually being given an a and b, we're actually just told to use the zero. So we have to do a little bit of extra work. We have to figure out what those zeros are for this quadratic function, which is simple enough. We can factor. So I need factors of positive 2 that add to make negative 3. Those would be negative 2 and negative 1. So we get x minus 2, x minus 1 as our factors. So my zeros are positive 1 and 2. So that becomes my interval. Those are my a and b values. So let's go through our conditions. So f is continuous on the interval because we know it's continuous everywhere because it's a polynomial. F is differentiable on the interval because it's differentiable everywhere because we know it's a polynomial. Then our third condition, f of 1 needs to be equal to f of 2. Well, we know that's true because those are the zeros of this function. So we know that both of those are equal to 0. So the third condition checks out. So by Rolle's theorem, we know that f prime must equal 0 somewhere. We just now have to figure out where that is. So we just used Rolle's theorem to guarantee our end result, that f prime equals 0. So now we can use that to figure out where it actually exists. If this didn't check out and we couldn't prove that it exists for sure, then we might not even waste time trying to look for it. So f prime in this case would give me 2x minus 3. And now I can set that guy equal to 0, add 3, divide by 2, and we get 3 halves, which is in between 1 and 2. So just to give you a visual representation of this guy, let's change this to x squared minus 3x plus 2. Whoops, plus 2. So I'm going to change my a and b values because now I know that it is 1 and 2. So there's my little interval. It's not a big portion of the graph, but again, they have the same y value. So this blue line is actually the secant line. You guys can see here I created the slope through those 2 points. So then you guys can see here, again, what Rolle's theorem is guaranteeing, or really mean value in general, is there's no way that these endpoints connect and create their slope without the tangent line at some point having to match that. So this C value is just changing the point of tangency on this guy. And you can see eventually it's going to have that 0 slope. Let me edit this step just to make it snap a little bit for me. You can see, and it happens to be right at x equals 1.5, that is where that tangent line's slope matches. And again, we could change this interval. We don't have to do just at the zeros. If I wanted to do a mean value theorem problem, again, the only difference between mean value and Rolle's is, are those endpoints equal to one another? So now the function hasn't changed. So the first 2 conditions are still true. It's still continuous and differentiable. So there's no way that those 2 endpoints produce a positive slope line of positive 1 without, at some point in between those, that tangent line matching that same slope. So boom, there we go. At x equals 2, those lines are now parallel. Those 2 slopes are equal to one another. So this is going to be true for no matter what the function looks like. Like I can just change this to a negative slope now. I might have to adjust my a and b's a little bit and zoom out. But no matter what interval we choose, because again, this function is continuous and differentiable everywhere. So I can make the interval anything, and there's going to be some c value in between that the tangent line will end up being parallel. Now, I may have, actually, nope, that works right there. At x equals 0, now those 2 are parallel, which again just means slope of the secant is equal to the slope of the tangent. Again, the power of this is it allows us to know for sure that the derivative equals a particular value. Sometimes it's the slope of whatever the secant line is. Other times when we use Rolle's, we want that slope to be equal to 0, and that's a powerful thing for us to identify that has to be out there. So it helps us know when we can actually look for it. Okay, so let's try one more. I've got f of x equals x to the 4th minus 2x squared. We want to find all values of c in the interval -2 to 2 such that f prime of c equals 0. So you can tell that this sounds a little bit different. And nowhere in here did it say use Rolle's theorem or use mean value theorem. But you guys need to be aware of, if I want to try and prove the existence of a particular value of f prime, we need to actually apply mean value or Rolle's. So it really just comes down to, what am I trying to set the derivative equal to? If I said prove or find all values of c where f prime equals 2, well, then that would be mean value. But because I want it to equal 0, this is us trying to use Rolle's. But first we need to check to see, can we use Rolle's? So first condition, continuity. F of x is another polynomial, 4th degree in this case, so it's continuous everywhere. Second condition, differentiability. Again, polynomial, differentiable everywhere. Third condition, does f of -2 equal f of +2? So for that, we're not told that these are zeros. We need to just check to see, are these going to produce the same value? Because it's not always going to be using the zeros of the function. That was just a particular case because you know for sure at the zeros, the 2 endpoints have the same y value. So this could turn out to equal something else. So let's check it. F of -2 would be -2 to the 4th is 16 minus 2 times -2 squared. So we get -8. So that equals 8 for the first side. Now for f of positive 2, 2 to the fourth is 16 again. 2 times 2 squared is also 8. So we do, in fact, get both endpoints to equal the same y value. So because of that, again, this is what guarantees the slope of the tangent must equal 0 at some value of x. Okay? So that was us just applying Rolle's theorem. It's guaranteeing that this has to be true at some point. Now we can go and actually figure out where that is. So f prime of x in this case would be 4x cubed minus 4x. Let's set that guy equal to 0. Again, this is the value that Rolle's theorem just guaranteed must exist at some value of x. And now we factor this guy. We've got a GCF of 4x. We are left with x squared minus 1. We could factor that guy, but this is also just solved by square roots. So this will produce x equals 0, x squared minus 1 equals 0, or x squared equals 1. So x equals positive or negative 1 after I square root both sides. So now we just got to check, are all of those values within our interval? In this case, they are. So that means there are 3 different points where this graph actually has a 0 slope. So let's go back to Desmos and check out what this guy looks like. So we have x to the fourth minus, fourth power minus 2x squared. And we are looking at our interval from -2 to 2. Okay. So we still see the general shape of this graph. It looks like a W. So there are endpoints, okay? And again, because they're equal to one another, we have 0 slope. So we're looking for where within that interval does this tangent line have the same slope as the secant line. So again, the 0 slope is where the graph is going to change directions. Every time the graph changes directions, we have 0 slope. Those are our relative extrema. So in this case, that occurs down here first when x is -1, then again at 0 at the origin, and then again at x equals +1. So there are the 3 places that we were looking for.